So, dear students, let us continue our discussion on atomic absorption. In the last class I had told you about atomic absorption spectrometry, the phenomenon, how it was discovered, etc. by Wollaston in 1802. Subsequently, Brewster put forward the idea that these dark spots, the lines denoted till then by alphabetical orders, must be due to the presence of vapors of certain elements in the sun's atmosphere. So, what it follows is the confirmation of quantum mechanical theory that the atoms absorption and emission of the radiation is a quantumized system, and the absorption of the vapors by the atoms causes the dark lines in the bright background of the suns. This phenomenon was known as Kirchhoff's law. It was used to deduce the presence of oxygen, hydrogen, sodium, iron, calcium, etc. in the solar spectrum. The experimental confirmation of this came from electric arc or spark, which was used to generate very high temperatures, and when the vapors were introduced into the arc or spark, they also showed, the spectrum showed dark lines similar to the radiations observed in the sun's solar spectrum. So, this is what I had shown you in the last class, that the how the solar Fraunhofer lines are visible. You can see at the bottom that there are dark lines in the bright background, and these are the different elements that have been detected: calcium, holmium, calcium, iron, and all these. These lines correspond to definite frequencies of the elements spectrum, which have been recorded elsewhere also. So, all we assume that in the solar atmosphere all these elements are present. So, in 1902, Wood repeated the experiments of Kirchhoff and Foucault and proved conclusively that by introducing the sodium vapor in the optical path of emission lines, a reduction in the intensity of radiation occurs. Now, you may be aware of this phenomenon in your day-to-day life also. For example, if you take a walk around your town in the night, whenever people use atomic these street lamps, use sodium vapor lamps, they are known as sodium vapor lamps. The sodium vapor lamps, sometimes you will observe that they are flickering. Sometimes it gives bright light and then stops, it becomes dark, and again it picks up, again it picks up. This is due to the absorption of sodium vapor. Usually what happens in sodium vapor lamp is there is a small amount of sodium kept in the street lamps, and that when we heat it by electrical heating, it gives out emission. So, the emitted light is yellow light, that you would see in all towns wherever they use sodium vapor lamps. Usually there are two types of lamps in the street. One is mercury vapor lamp, which will give you very bright white light, and other is sodium vapor lamps. So, these sodium vapor lamps keep on occurring on and off. Many people who do not know about it think that electric supply is erratic. Actually, it is not so. Quite often once the sodium kept in the street lamp evaporates, that vapor will absorb its own radiation, and then the intensity of the light becomes less. So, this is a phenomenon which is very commonly observed, but when we during in Wood's time, that is in 1902, this phenomenon was observed, but by analogy with acoustic resonance lines, what he showed is the possibility that these resonance effects can be used to detect traces of mercury. The potential of this technique actually was not recognized by analytical scientists and spectroscopists also till 1924. Later on, they somewhere around 1913 somebody showed that mercury can be determined up to 10 raised to minus 13 grams in the environment using this technique. But as an analytical technique in the laboratory, it was not available for another 30-40 years. So, continuing our discussion, Angerer and Jose published the atomic spectra of the iron group metals, followed by Freyne and Smita for indium, aluminum, gallium and tantalum. Müller and Pringsheim in 1930 published the first atomic absorption method of measuring the mercury content in the air. Even this did not evoke interest in analytical chemists for the determination of other elements, because the a simple common laboratory instrument was not available for the determination of all metals. One or two metals in the research laboratories, it is okay, but if any analytical technique is not available in every laboratory, that is not a universal technique. So, until an instrument was developed to determine all these elements, atomic absorption remained as a curiosity only as far as the chemical analysis was concerned. So, Walsh was the person who discovered analytical potentials of atomic absorption, and then he developed the first real application of atomic absorption to chemical analysis. That was in 1955. So, somewhere in Walsh is an Australian scientist. You will find this information in several textbooks, but what is important is in the same year Alcamade and Mietz described a double beam method of spectral selection with two flames, the first being the source and the second is the atomizer. So, we will see what is source and atomizer and other aspects of atomic absorption shortly. But ever since the Walsh developed this analytical technique, the atomic absorption spectrometry is in the forefront of chemical analysis. The first commercial atomic absorption instruments appeared in 1960s. Somewhere around 1970s, they were there in several laboratories, and by about 65 or so instruments were available in India, and right from 1970s onwards, almost every university in India and elsewhere have got atomic absorption spectrometers in their laboratories for the determination of metals. So, spectacular advances in instrumentation, electronics, automation and computers have taken over the complete overhauling of atomic absorption spectrometers, and they have made atomic absorption spectrometry one of the most reliable techniques of modern times, perhaps equalled only by atomic emission spectrometry in terms of simplicity, sensitivity, specificity and speed of operation. The most important aspect of atomic absorption spectrometry is its specificity. That means, if the element is there, it is detected; if it is not there, it is not detected. So, not only it is used for pass and fail tests, but also for the detection of metals, and determination of course is meant to be by quantitation of the radiation. So, the further development of atomic absorption was by Professor Labov and Massmann. I had the opportunity to meet the Professor Labov and Massmann sometime back in 80s, and these two gentlemen, Professor Labov is from Russia and Professor Massmann is from Germany. Both of them pushed the detection limits of atomic absorption to nanogram levels and picogram levels, sometimes even up to femtogram levels. That is, I had already explained to you that it is up to 10 raised to minus 15 grams. Then came another development, that is hydride generation atomic absorption spectrometry. This technique could be used only for elements which produce hydrides, metal hydrides. These elements include arsenic, antimony, bismuth, selenium, tellurium, germanium, lead and lead. So, but it is rarely used for lead nowadays, but for arsenic, antimony, bismuth, selenium, tellurium and germanium, in parts per billion level analysis, only hydride generation atomic absorption spectrometry is being used even now all over the world. So, it is a very important development. We will be studying it in the course of this program. And cold vapor mercury determination, that is another extension of the atomic absorption, and that also has been nowadays pushed to the forefront of mercury determination up to 10 raised to minus 12 quantitatively. That means 2 into 10 raised to minus 12, 5 into 10 raised to minus 12 grams of mercury can be determined, not detected. They can be determined quantitatively with accuracy and assurance, and such advances have proved the attractiveness of the atomic absorption technique to make it the first choice of analytical scientists throughout the world. So, the popularity of atomic absorption spectrometry, you can gauge it by the fact that more than 100 books have been written on atomic absorption spectrometry so far, more than 100, and then more than 10,000 publications have been have appeared in leading journals of analytical science and chemical analysis. Chemical there are journals, scientific journals dedicated to atomic absorption also. Nowadays they are there, and more than 5,000 symposia, conferences and all the workshops have been conducted till date. They have appeared with applications in biological, chemical sciences, nuclear sciences, industrial products, soils and environment, etc. So, you should be feel happy that we are studying one of the most versatile techniques that will equip you for any job that you may undertake after your degree if you are taking this course, because I am going to make you an expert on atomic absorption spectrometry by the time we are through with each other. So, please learn the subject very carefully and wish you all the best. We continue our discussion on the theoretical concepts of atomic absorption now, because so far I have given you only a small introduction of the atomic absorption spectrometry. Now, what is that is important in atomic absorption? What are the basic concepts we have to learn? So, the simplest concept of atomic structure which we have already studied is that there is a positively charged nucleus containing protons and neutrons surrounded by an equal number of electrons orbiting in space in the electric field generated by the protons. Okay. That means, in any atomic structure there is proton is carrying large amount of electric weight, and there is an electric field, positive electric field generated around the nucleus, and this positive electric field is neutralized by an equal number of electrons in terms of electrical charges, but weight of the electrons are, they do not match with that of protons. So, the electrons are going round and round to balance the total electrical charge around an atom. So, according to the quantum mechanics, such a system can exist in stable state only if its energy is quantized. This we have already studied, and even at the lowest energy level or ground state. That means, the atoms must be, the quantized atomic energy is quantized at the lowest energy level or at the ground state or at room temperature. All other levels are excited levels. This means the electrons in the ground state of the atoms, this can be excited to higher energy level, because all other elements, all other electrons are at the ground state at room temperature in the in a general system. For example, in this room there is wood, there is metal, and wherever there is metal, all the metal elements in this room, or wherever you are sitting on the chair or your clock or anything that contains the metal, all the atoms in that unit are at the ground state without, there is no energy exchange, but all the electrons are at the ground state. Now, if I supply certain amount of energy, that means I can excite all the electrons to the next higher energy level. That is what it means. So, how do we do that? We can do it by inducing electrical energy or mechanical energy, or I can simply heat it. So, the energies associated with these systems are in the range of few electronic volts, that is represented by a Gaussian diagram. So, what is a Gaussian diagram? That I will show you in the next slide. This is the Gaussian diagram, energy level of sodium. You can see on the left side, you can see on the left side I have plotted electron volts, that is ground level is 0 and then 1, 2, 3, 4, 5 etc. and these are the energy levels of the sodium atom. So, what are these energy levels? That is 2s by 1 and half, 2p 1 and half, 2p 3 by 2, 2d 3 by 2, 2d s by 2, 2f s by 2, 2f 7 by 2, like that. These are the energy levels. That means there is one electron, in the outermost orbital of the sodium atom. You can look up the structure of sodium atom, it has got 23 atomic absorption etc. It is in the outermost orbital there is only one electron. That one electron is having a spin of half, spin quantum number is half, but there are combined effects of the orbitals, and those orbitals are designated as s and p orbitals, s, p, d, f etc. This I have already explained to you in the earlier classes. So, for sodium it is 2s half, 2p half, 2p 3 by 2, 2d 3 by 2, like that. There will be different energy levels to which an electron can be excited. This is the ground state, that is 3s. Okay. So, 3s can be excited, that is the ground state, and when the electrons are excited it goes to 2s by 2 etc. That is these s and this s are different. You should understand, I have written here 3s in the small letter, here I have written 2s in the capital letter. That means these energy levels are not the same. So, do not confuse that how it can happen from 3s to 2s, that is different entirely. So, the current energy levels, if the electron is to be excited, it will go from 2s half to 2p 3 by 2, 2p 1 2p by 2 and 2p 3 by 2, 2d 3 by 2 etc. So, the energy levels, if I take sodium atom and excite it, I will get frequency lines corresponding to this. I have shown you different parallel lines here, and 3s is the ground state. Okay. From 3s it goes up to 3p. Here I am showing you it is 3p. Okay. And then there is 4s is here, and then 4p is here, 3d, and there are other 4f etc. other energy levels are shown all around here. So, the ground state electrons are at 3s. So, if I start giving energy to this, I get different spectrum. If the electron goes from 3s to this line, somewhere around I supply 4.5 volts, the electron will jump to this higher this level from ground state, and that corresponds to 268.0 nanometer energy. Similarly, if it goes here, it is 285.3 nanometers. Next is 330.3, less energy I am supplying, and then there is another one 330.2, and then 589.6, that is around 2 electron volts, and if it goes to 3p, that is also approximately same, that is 589.0. That means the electrons in the atomic absorption spectrometry, whenever I am talking about the excitation of atoms, what I mean is this. That means electrons will be excited to from 2s to 3s to 3p, 3d, 4p etc. But again, when I am supplying, I have shown you in this figure, some of them are dark lines and some of them are thin lines. If you observe this figure carefully, you can see that some of them I have shown as dark lines and some of them are very thin lines. So, these dark lines are known as resonance lines. Okay. So, these resonance lines, what do they represent is the energy can be supplied from 3s to 3p, and if I have an electron at 3p level, it can absorb vapor and then it can lose its energy and come back to ground state. That means absorption and energy will occur at the same wavelength. I have shown it by double lines, double arrows. So, the lowest energy state is known as resonance line. This resonance line is basically, it shows us that if I have a vapor, I supply energy, the vapor can absorb that energy and come down to the ground state, or if I have a ground state atom, I supply this much energy to excite the electron from this level to this level, higher next resonance level. There are 1, 2, 3, 4 resonance lines in this spectrum of sodium, but you will see that in 3p there are 2 lines, one is 589.6, another is 589.0. That means, both these lines are very near each other. That means, quite often if I do not have a good spectrometer, it means that both lines will appear as single line, but if I apply a magnetic field I can separate them. So, you will see two spectrums, two peaks. So, this is the fundamental basis of all atomic absorption spectrometry. All other elements will show, if you take the spectrum and plot electronic volts and energy levels like this, all of them will look approximately similar like this, but for the only difference is the energy levels will be different for each element. So, that is how the Gaussian diagram for a atomic absorption looks like. So, what happens here? Emission of light occurs when an atom reverts to a state of lower energy. Okay. If an atom is at higher energy level, it falls down, it has to lose its energy, sometimes it is emission. So, from higher to lower energy there is emission, lower energy to higher energy it absorbs the radiation. So, Bohr's expression expresses the conservation of energy by a simple relation, that is E2 minus E1 is equal to h mu. So, you look at this figure, I have written the same thing, the frequency, that is wavelength, is expressed by the energy difference between the two divided by Planck's constant, or since frequency is related to wavelength, which is a very measurable quantity. Simply for atomic absorption, lambda is nothing but velocity of light divided by frequency, that is the wavelength is given by hc divided by the energy difference, that is E1 minus E2. So, in this expression, c is the velocity of light, this you know, h is the Planck's constant, it is a universal constant, that is 6.62 into 10 raised to minus 4 unit 34 in SI units, mu is the frequency, lambda is the wavelength, and E1 and E2 are the energy levels of excited and ground states. I think you are all familiar and comfortable with so far. Okay. So, inserting the numerical values, what do we get? You put all those numbers and you get lambda is equal to 1.23978 and divided by delta E. Delta E is nothing but E2 minus E1, that is energy levels, difference of the energy levels. So, a transition from the resonance level of sodium, that is occurs at 2.102 electron volts to the ground state, that would correspond to the emission of 1.23972 divided by 2.102, that is the energy, that corresponds to 0.5986 micrometer or 589.6 nanometers. I have given you the conversion of micrometer, nanometer, etc. in a table in the earlier version, earlier classes. Okay. So, there should not be any confusion with respect to this. So, when a photon of frequency mu interacts with an atom of energy E2, the atom may be able to absorb the photon. So, it goes to E2 plus h mu, that is some amount of energy is absorbed and it goes to next ion, the difference is h mu. Okay. So, provided the new energy level is equal to the one of the excited energy levels. In between energy, if you supply, nothing happens, that is the beauty of quantum mechanics. So, we write this expression E2 mu is equal to E2 E1 minus E2 by h. So, compare this equation with first one here, it is same. Okay. So, an atom can absorb, what it means? An absorption can also happen, an emission can also happen with using the same amount of energy depending upon where the atom is there. So, if the atom is at higher state, it has only to absorb, to come down to lower energy level and emit the radiation, and that is, it has to emit to come down to lower energy level. If it is at lower energy level, it has to absorb to go to the next higher energy level, and both the energies are same for excitation and emission. So, comparison of both equations shows that an atom can only absorb the radiation that it is able to emit. Okay. That means, if it is able to absorb, it can also emit. This is the beauty of Fraunhofer lines, because in the sun's atmosphere at around 2 million degree Kelvin, everything is in vapor phase only, but they can absorb the radiation, other radiation corresponding to that their excitation energy levels, and the concentration becomes less. So, it appears as a dark line. So, this forms the basis of atomic absorption spectrometry also.